In this class, we go back to basics, specifically around finding derivatives. We're going to go to the very fundamentals of just how we do derivatives. We'll do a few quick fire questions around that. Then we'll move on to the more complicated scenarios where you have to use chain rule, product rule, or quotient rule. Enjoy. All right, let's make a start. So let's have a look at some derivative stuff. So basically what I'm going to do is I'm going to quickly introduce a basic topic around derivatives. We'll do a bunch of quick fire examples and then we'll move on to the next topic on derivatives. So first things first, the fundamentals of the derivative is the derivative table. So what we're doing here is we have some function f of x that is on our left-hand side. If you want to find the derivative of that function, you simply just identify it's this function, and so its derivative is this thing. So if I were to do the example of finding the derivative of x squared, I would say, okay, I have x squared here. That is a type of power function, x to the power of n. And so what I would do to find its derivative is bring that power of n down the front and reduce it by 1. So in this case, your power is 2, so 2 is going to come down the front. You're going to subtract 1 from the 2 up in the power to give you a final derivative of 2x there. So that will be a power function, derivative type. Another thing we could look at, derivative of exponential. So, in fact, before I get into that, it might be worth understanding the properties of the derivative. So, if you have more than one basic function in your function that you're trying to derive, then all you do is you go term by term, and you do find the derivative of each of those. So, in this case, you have 4 sine x and you have minus 2 log x. So if you want to find the derivative of this whole thing, the first property up here suggests that you can just find the derivative of each of those terms. So that's the first thing. The second thing is normally these coefficients, right, like these don't actually appear on our table of derivatives, right? There's no coefficient out the front of any of these. And so in theory, you can use this second property here, which is that you can take coefficients outside as a multiplication at the end. So instead of having the derivative of 4 sine x, you now have 4 times the derivative of sine x. And same thing over here. Instead of minus this, you now take that 2 out the front. As far as how you go from here, now when you want to do the derivative of sine x, you can look on your table. You can see d dx of sine x is cos x. So when we go down here, this entire term here gets replaced with a cos, and that 4 that was chilling out the front now comes through at the end. Similar with this, derivative of log is 1 over x, and so you replace that d dx of log with a 1 over x, and the 2 comes through at the end. Those are the basics on how you handle derivatives with multiple terms in here. Now we're just going to do a few quick fires. So what I'll do is I'll leave the table of derivatives up here. I'll make up some random functions, and then we're going to find the derivatives of those. So let's go with y equals cos x minus 2 natural log x. We want to find the derivative of this. What might we start doing? You are muted, by the way, I will just say that.
Should we find the derivative?
Yep, so we're going to try and find our derivative, absolutely. What does that start looking like?
So if we distribute the d over dx, like, no, not distribute that. Like cos x becomes negative sine x,
Yep, that's it.
and then natural log of x, it should become negative 2 over x.
Yeah, that's exactly right, negative 2 over x. You could bring the minus all the way out the front there, but otherwise, yeah, that's exactly it. So you just look on the table and you replace the terms. That's one of them. We'll do another few examples. So let's go with 4 e to the x, and we'll chuck in a, what's another one? Let's go tan. Why not? Tan x. I want to find the derivative of this. What am I doing?
So the 4 e to the x stays the same,
Yep, that's it.
and then the tan x becomes 1 over cos squared x.
Exactly right, yeah. 1 over cos squared x. Cool, and that's our full derivative there. So basically, just using the raw table of derivatives there, you use that anytime you have, let's call it, you have y equals a f of x plus or minus b g of x. So you might have a bunch of different functions. They might have some coefficients out the front. Under those circumstances, you can always solve that just by looking at your table of derivatives and then just replacing the terms as required. Do you want to do any more quick fires there, or shall we move on?
I'll move on.
Okay, cool. Where it starts getting a bit more complicated is when the inside of the brackets is anything other than just x. So the example I give on the screen share now is natural log of x squared. That is not a match on this table. There's no algebra for you to, there's no algebra to be done there as far as, well actually, that's a lie. You can use the log laws there. That's actually an exception. I just realized that now. If it was anything else, there would be no real algebra to make it look like this. And so basically the idea is that as soon as anything other than just x inside the brackets of your function, or where there would normally be just an x, that's a chain rule. So otherwise known as a composite function, right? Some f of g, where g is your inner and f is your outer. Under those circumstances, you want to split up your function into two sections. I've used g in the notes. A lot of the time people will use u. Point being, you take whatever the composite part of your composite function is, and you take that out as your own term, as its own little function. That gives you g of x as its own function. What you want to do from there is rewrite your function f purely in terms of g. And you'll know you've done it right when you rewrite this and you get a perfect match on the table. So natural log of g is this, right? It says g instead of x, but it's a one-to-one match as far as like the actual overall format of the function is. So that's your indicator for if you've actually done chain rule correctly there, or at least started the chain rule correctly. From there, you have your f of g, you have your g of x, you find derivatives of each of those. So again, looking up your table of derivatives, now we're just doing more of what we just did already. X squared becomes 2x, natural log always became 1 over the g. Once you have those two things, chain rule is this. dy on dx, so derivative of this whole thing, is dg on dx multiplied by dy on dg. This is dg on dx, it's derivative of g with respect to x. This is dy on dg, derivative of y with respect to g. So it says to multiply those two things together, and so that's what we'll do. This multiplied by this, and that's what this ends up looking like here. 2x over g, where g was x squared. You just want to make sure you put that back in at the end. And then obviously do any further simplifications if at all necessary. Anything to clarify there, or shall we do some chain rules? I'll start drawing some up if... Okay. So what I'll do is, what would be best to have up? I think this one will be best to have up, and I'll have a screenshot of the table of derivatives in the comments, so you can, well, I should have taken a better screenshot instead of cutting it off like that. Let's try that again. Cool. All right. So if you need to refer to the table of derivatives, that'll be in the chat. Otherwise, we shall continue on with this. So we'll say, what's a good one? We'll have sine of 3x there. We want to find the derivative of sine 3x. So first things first, do we need to use chain rule? And if so, why?
Do we need to use it because the thing inside the brackets is not x?
Correct.
More
Absolutely.
than x.
Yeah, it's a 3x, not an x. And so from that point onwards, we now know we have to use our chain rule. How do we use chain rule?
Should we get like another variable like g of x is equal to 3x. So
Sounds good to me. G of x is 3x. What else do we need?
then we need to find g dash of x,
G dash. Yep. All right. What's that?
3.
Absolutely. What else?
Hold on. We need to find f of g
Yep. F of g.
or
That's it.
y of g,
Yeah.
sort of.
Either way. Y of g. Those are two very bad letters for my handwriting, apparently. They look very similar. There we go. Y of g. So what's that going to look like?
Sine of g.
Absolutely. And what's the thing to look out for to make sure you've done the right substitution there?
Um, Not sure.
Not sure. So basically, the idea is, can you look at this and find it on your table of derivatives, like basically 1-to-1? If there was still anything left over, like if it said 2g in there, or if it said anything else, then you would have done the substitution incorrectly. However, this one is a direct match. You assume that g and x are the same thing as far as the table is concerned. Point being, there should be no lingering coefficients on here, which is what we have. So we've done it correctly. What do we need to do now that we have y of g?
Y dash of g.
Y dash of g, that's it. And so this should require no real effort because you just look on the table. What's that going to be?
Is that cos of g?
Yep, sine goes to cos. Precisely. We have everything we need. What are we got to do to put it all together?
We got to multiply
Yep.
the f dash of g and g dash of x.
Yep. Those two together, absolutely. So 3 cos g. Anything else to wrap it all up?
Look for simplifications if there are any.
Yeah, I'll make it a bit clearer what we have to do by rewriting the function. We're trying to find y dash of x. That's our goal. So what's...
Bring x back in.
Yeah, precisely. So final line is going to look like what?
Will it just be 3 cos 3x?
That's it. Yeah, because g was 3x. That's what we assigned it. That's it. That's chain rule. So the real challenge is in identifying the composite function, and then from there, well, if you can see it's a composite function, you just follow the procedure. So I'll put together a few more. In fact, what I'll do is I'll do a combination of two functions. What have we not touched for a little bit? Yeah, we'll chuck a power function in there. Y equals 2x minus 3 all squared. And then we'll have... I guess they're all kind of similar, huh? Plus natural log. Nah, I've already done a natural log. We'll do a cos. Here's a weird one. Cos x on 2. Okay. What are we doing with that?
First we can just find the derivative of 2x minus 3 squared.
Yep.
Which is 4x minus 6.
4x minus 6. Where did that come from? 4x minus 6?
I just dropped the power down and then distributed it.
So you did 2 at the front, 2x minus 3, and then like that?
Yeah, I'm not sure if that's right there.
It's mostly right. Point being, is this just x inside of the brackets?
There's a constant as well.
Yeah, so there's a constant and there's also a coefficient as well. And so the point I'm trying to make is that this isn't a power function just yet, not until we use the chain rule on it anyway. So what's wrong there is we need to take this thing out the front and call it, let's say, g. Right? G of x is going to be 2x minus 3. And then from there, well, now we're in a bit of a pickle. I'm going to call this thing u, and I'll call this thing z, whatever, just so we know what we're talking about. So if we're trying to find the derivative of just this term right now, you'd have to rewrite this. So u of g is now g squared. So This you can just do power down the front, reduce it by 1. This, not quite, because there was stuff inside there. There is no match on this table of derivatives to actually achieve just power down the front, reduce it by 1. But okay, now that we know we're trying to do chain rule on this, how do we follow this up?
Do we find g dash of x?
Yep, g dash x, which is
2x.
close.
Oh, sorry, no, it's just 2.
Yeah, that's it. And then what else do we need?
We need a, like the z term, we need to find derivative of that as well.
Yes, that'll be on its own. We'll do that bit later. We'll just focus on getting the derivative of u right now, and then we can move on to that. So this itself is a chain rule. This itself is also a chain rule. So basically doing 2 in 1, really. So we'll focus on this one first, then we'll get the other one done. So this one we split up into g and u, u of g rather. And so if we want to complete the chain rule of this, we need u dash of g here, which is what?
R2g.
2g, yeah. And then to finish off the chain rule, how do we do that?
We multiply u dash of g with g dash of x.
That's it. So we would say u dash of x, so derivative of this thing specifically, would be 2 times 2 is 4, and then the g is going to stay there. Lastly, we've got to do one final thing, which is what?
Oh, we've got to bring it back into the function.
Yeah,
No, so bring x back in.
that's it. So g was 2x minus 3, and so what we're going to do is expand that all the way out, ax minus 12. So basically, all that was missing there was, instead of just doing power in the front, reduce it by 1, you also need to multiply by the derivative of the inner, which is 2. So, very similar result, you would just out by a factor of 2 because of the chain rule. But okay, that's the derivative of that first term there. Y is also made up of this term as well. Question now becomes, how do we do chain rule on this?
Would we just start off with like establishing like a h of x or something like that for
Yep.
x over 2?
Yep, h of x is going to be x over 2. From there, what else?
Now we find h dash of x.
Yep, h dash x. Oh, sorry, I don't know why I put that over there. H dash of x is what?
Is it just 1?
Well, let's think about it for a moment. This is the same as saying a half times x. Does that change your mind?
I think it's still 1.
Still 1. So the way you do linear is there's an implied 1 at the front here of that power. And so power goes down the front and gets reduced by 1. So you have 1 times a half times x to the power of 1 minus 1, so 0. X to the 0 is 1. Another 1 over here. Anything times 1 is just itself. So you're going to leave with that half there. So basically, anytime you have anytime you have a linear, the derivative of that linear is always just going to be its coefficient out the front. Clear enough?
Yeah, right.
Okay, that's h dash x. And then what else do we need for finishing up chain rule?
We like z of h.
Yep, z of h. That's good. Z of h. So z was the function we're trying to derive, and we take a substitution out of that. So z of h, if I were to rewrite that, what does z of h actually look like? I guess a reminder that h is over here, and z is here.
Is it h over 2?
Wouldn't be h over 2, it would just be h, because remember h is x over 2, so you're replacing x over 2 with the letter h. So we're just going to say cos h, like that. It was kind of nasty of me to point this one out. It made it look like you had to do something here, but really it was just, like you can see over here, we just used the letter g because g replaced all this. Same thing here, h was that, so we're going to replace it with h. But okay, we have our z of h. And again, remember the litmus test is, can I spot this thing directly on my table of derivatives? If you had h over 2 here, you would know that you've done something wrong because that doesn't actually match anywhere. But okay, we've got it. So next step is what?
Find z dash of h.
That's it. Z dash of h is what?
Is it sine?
Check your, yeah,
Negative sine. Wait, give me a second. I'm trying to find the table. Negative sine of h.
yeah, that's it. So you never have to memorize those, by the way. It'll always be on your table as far as like a reference sheet goes. It'll be on your formula sheet. That's tech free and tech active. So no worries on not knowing exactly what those are. And then yeah, just finish off with that multiplication. So we know, let's see, what was this called again? Z of x. Z of x is now a half times negative sine h. So negative a half sine, and well, h is x over 2. So we're just going to put that out exactly as it was. So we've done derivatives of each of those individual terms. Reminder that y was an addition of those two things. So derivative of u replaces this spot, derivative of z replaces this spot. So our final y dash is now, well, maybe I should say y dash of x. In fact, really I should be saying dy on dx. Like, that's the real notation. Sometimes I get a bit lazy with it. Dy on dx is going to be the linear, so 8x minus 12, that's our u dash, and then our z dash minus half sine x over 2. So any one of those individually is fine to do individually, as long as you can identify it's a chain rule situation. Doing them together, you can see it kind of gets a little bit messy. So being very specific with labeling your terms is a good idea there. All right, so we've done effectively maybe 3 or 4 chain rules there. Anyone want to see any more chain rules, or shall we move on to the next bit? I'll just pause for like a minute to have a drink. All right, cool. Next derivative up. Product rule. So far we've looked at how to handle regular old derivatives, and we've looked at how to handle composite function derivatives, whenever you have something inside of another function. What we're going to look at now is what happens when two things are multiplied together. So basically, this is where you need to be really sure about like what's on your table of derivatives. If you can identify any multiplication between any two of these things on the table, 2 or more actually, but very rarely anything more, then you have a product rule. So it could be e to the x times sine x. It could be log times x to the power of n. It could be tan times cos, right? What's different is if I said log of sine, right? Putting a sign in here. So being aware of where the terms are located, just because it's inside of a bracket doesn't necessarily mean multiplication, because all of these here, these functions don't exist without their brackets. So I know this trips up a lot of people, which is it a composite function or is it a multiplication? Look back at this table. Does that function exist without its brackets? If the answer is no, then that is in fact probably going to be a composite function, because putting something in here is not a multiplication. So that's the thing I'll be looking out for. In this case, look, you've got individual functions here. You've got x squared multiplied by sine x. And so, because you're able to identify power function and circular function multiplied together, product rule is required. How do we do it? Well, this is what's going to appear on your table, on your formula sheet, whether it's tech-free or tech-active. I think they have the terms back to front. They have u and then v. I have v and then u. It doesn't matter though, because it's multiplication and it's addition. Point being, you should be able to see this and realize, okay, that's two things that are multiplied together. So v is going to be one of those things and u is going to be the other thing. So in this case, I've got v as x squared and u as sine x. It doesn't matter if you change what u and v is, at least for this type of function. But okay. Product rule says I need v and u. Cool, I've already got that. But it also says I need derivative of u and derivative of v. That I don't yet have. But I know how to find them pretty quickly because these are direct matches on my table. X squared becomes 2x, sine becomes cos. Then from there, I just follow the notes rather. So it says do v times u dash, it says u times v dash, and so that's exactly what I'll do. Here's my v, which is x squared. Here's my u dash, which is cos x, so on and so forth. Just plug them in, and the vast majority of the time, that just is your final answer. No more simplification required. You have two options, which is you either fully expand or you fully factorize. And depending on how complicated what you have is, you may elect for one or the other there. Anything to clarify there? Or shall we get into some product rules? I'll start writing one up in the meantime. All right, no questions. Let's get into it then. So, what I have here is y equals e to the x natural log x. So, do we need to use product rule here? And if so, why?
We have to use it because it's like y is a combination, like a product of two different functions.
Indeed. Now, here's a follow-up question. We won't actually do this one just yet, but what if I did this? What rule or rules would be required now?
Is it chain rule because the exponent isn't an x?
Yeah. So, but there's still a product in there, isn't there? It's a e to the 2x multiplied by natural log. So what that would now look like is, broadly speaking, this is two things that are multiplied together. So you've got to start by splitting them out. U equals e2x, and then v equals natural log x. However, when it comes to finding derivative of this is now chain rule. So really, me putting anything anywhere else here shouldn't actually change how you look at this initially, which is you definitely start with product rule, but now that we have to find the derivative of this is a chain rule situation. Clear enough why both would be required now? To make things simpler, we'll start off with just two basic functions on the table, and then we'll get into some more complicated ones once we've got the mechanics boiled down. So we have our u, we have our v. What are we doing with them?
We find the derivatives.
Yeah, derivatives. So derivative of u, what's going
It
on
should
there?
stay the same.
Yep. Derivative of v,
Is it 1 over x, I think?
1 over x. Yep. Now, for the fun bit, how do I actually smack them together?
We have to multiply u with v dash and then v with u dash and then add them together.
Yeah, correct. So this is what's usually referred to as the cross product. If you align your notes in the way that I'm aligning them, it just means you multiply along the diagonals and you add the results. So you're going to have e to the x multiplied by 1 over x, e to the x, 1 over x. plus separates them, e to the x natural log x. You got a couple of options. You could put, since this is somewhat factorized, you'll either start by, or you could either finish it off by expanding it out like this, plus e to the x natural log x. But that kind of looks a bit weird, and so typically you would take an e to the x out the front. Now, this is still fine. You will get the answer correct if you do this, but more typical is take the factor of e to the x out the front, and then you can have 1 over x plus natural log x. If you don't like the fraction on its own, you can even chuck this up the top by going e to the x 1 plus x natural log x all over x. So to do that, I'm just multiplying natural log x by x and then dividing by x. You can see if I cancel that out, I get back to where I started. Now, pretty much all of this is fine. You could leave it here, you could leave it here, you could leave it here. All of that's fairly well to leave there. Okay, so that's one product rule done. Let's go with another one. Y equals, what else have we not done? Yeah, let's chuck a tan in there. Tan x squared. No, we don't know how you pay x squared. Let's make it slightly harder with a 3 instead of a 2. Alright, what's going on here?
U is tan of x and then V is x over 3.
Yep. U is tan x. V is x cubed. What else?
Then like U dash is equal to 1 over cos squared x, I think.
Yep, that's good.
And then V dash is 3x.
3x something, not just 3x.
And then we just multiply.
Well, hang on. It might have cut out a little bit. Yeah,
Oh,
P is
my.
right, 3x squared. Did yours cut out?
Yeah, sorry.
Ah, okay. No worries. And then, yeah, just multiply. So, yeah, maybe a bit harder to say this one out loud, but yes, yeah, multiply along these diagonals. So you're going to have 3x squared multiplied by tan x, and then you're going to have, yeah, okay, that's a bit nasty-ish. I'd probably just put x cubed in the top, and then cos squared x on bottom. Here, yep, there's not really a whole lot left to do. Yeah, you could go and take x squared out the front of all this and then put same denominator again, but yeah, it's a lot of work for not a lot of gain. It doesn't actually, it's not required per se. Alright, and now we'll do 1, which is going to be slightly harder. Y equals, okay, what have I not done yet? We'll put a cos 2x in there, and we'll chuck in, yeah, we'll chuck another e to the x in there. Why not? Alright, what's going on here?
U is cos 2x and then B is e to the x.
Yep, cos 2x, v e to the x. Now what's up?
So, like, we already know that V dash is going to remain the same, but then for U dash, we're going to perform chain rule.
Yes, there we go. See? Nice. So what I'll do at this point now, because we've done a fair few chain rules, is I'll show you the formula sheet that you actually get. So the ones in my notes, I've deliberately removed some of the stuff they give you because I want you to understand when and why to use chain rule. The formula sheets actually already solve a few basic chain rule forms for you already, I think at this point it's worth pointing that one out. So let me pull up one of the, I guess it doesn't matter which one I pull up. Well, except that one. That's an answer sheet. That's not going to have it. So this is what you'll get exactly in your exam. If we take a look at the screen share, you'll notice that theirs is a little bit different. You'll notice there's a whole bunch of A's in these spots, except for log. Log's a bit of a special case. A. So notice that they've actually done some chain rules for you. So they've done the case where you just have AX, or I guess in this one they have AX plus B. And you might notice some of the similarities, right? Like if you look at like sine AX here, sine becomes cos, the thing in the bracket stays the same, and the derivative comes out the front. So if I try to scroll back and find a time where we did a chain rule for, let's say, cos x on 2, if we look at z dash, for example, we had cos x on 2. As part of our formula sheet, it says that cos goes to negative sine, so that's happened. It's become negative sine. The thing at the front is the a value, which is the coefficient. So the coefficient was a half, and so a half came out the front. And it also says to just leave the brackets as they are. X over 2 was what we started with, and x over 2 is what we ended with. So it's solved some of these basic chain rules already for you, but it's good to know when and why to use chain rule. So that's that. So now, based on what we're seeing with this actual formula sheet, instead of going for a full tilt chain rule, what do we now have to immediately solve our derivative of cos?
We can just say that it's going to be equal to negative 2 sine 2x.
That's it, yeah. Negative 2 sine 2x. You'll see on the formula sheet you have cos ax, so a is clearly 2 if we compare the two things together, which means every a you replace as a 2, and well, that's actually really all it was. So that's a chain rule already solved. And then obviously, yeah, to finish off the product, you do your cross multiply. So y dash of x is therefore minus 2 e to the x sine 2x, and then this one over here, plus e to the x cos 2x. You might see me hesitate the order to put these things in. That's literally just because I'm pedantic about the way I write them. Like if I put e to the x here, I'll put e to the x at the front here. It doesn't matter the order. You write these things in. So that's just me being a bit weird. So yeah, that would be pretty much as complicated as product rule is going to get, where you have to do both product and chain rule in the same go. Alright, that's those. Last on the list is quotient rule. Good news is you basically do the exact same thing as you do in product rule. Bad news is what you do with those terms is a little bit nastier, because you're now not only doing vu dash and uv dash, but you're also dividing the whole thing by v squared, which is just a lot of writing. It's not actually difficult per se, because you actually just ignore the denominator until the very end. It just ends up being a lot of writing for no, well, it's just not nice. Anyway, so quotient rule. That's whenever you have a division of two functions. This one should be the easiest to identify because a fraction really makes itself known. It's like, yeah, I see a fraction there. I'm not gonna miss that anytime soon. And so the only thing to really keep in mind here is that u and v are very specifically placed. U has to be the numerator, v has to be the denominator, and that's made obvious in the actual like in the actual formula. U is in the top, V is on the bottom. It's exactly what it looks like in the, yeah, it's over here. U is on top, V is on bottom. That's what you'll exactly see in the formula sheet. But otherwise, we're doing the same stuff. Find derivatives of V and U, and then smack them into the spots that it says to smack them into. So in this case, we have natural log divided by x squared, and so U is going to be the natural log, V is going to be the x squared. From there, derivatives of each, x squared becomes 2x, and then natural log becomes 1 over x. This time when you do your cross product, you do a minus in between them. So VU dash is going to be x squared 1 over x, that's that, minus UV dash, so natural log, and then 2x in that order. I've put in what V actually was. You got to divide by V squared and all of these. Usually you can leave that until the very end. Like you can just write the letter V squared until the very end because it's unlikely that this will actually require or be helpful in simplifying anything. Like if we look at an example in the book for the quotient rule, even a pretty early on example, like if you have this e to the 2x plus 1 all squared, that's really not going to help you simplify anything, right? The chances of you having a factor across both terms being e to the 2x plus 1 is basically 0. So to save you some writing, just write v squared until the end. Another final tip on that is to never split the fraction. So you might look at like this example here and be like, oh cool, I see x plus 1, I see x plus 1 squared. If I were to split these up, then I could cancel that down. Yes, but you've also now got a nastier, you've got two sets of fractions with different denominators. It's just not nice to work with. So the other final tip is leave the fraction as is. Work all your effort on simplifying the numerator, and only at the end do you even bother with looking at denominator. But yes, just keep it all as the same fraction. So you'll see in some cases you can actually do something with it. Like this one here, there was an x here and an x here. So you can actually delete one of those x's because you have x to the 4 on the bottom. Oh, that's really annoying. I just realized that's like a page breakdown. Was there really no way to shrink this ever so slightly? Bugger. Oh well. Anyway. Anything to clarify there, or shall we get into some examples? I'll just take a sip of water while you think. Alright, let's make up a few more examples. Y equals sine... Oh, I was going to do something cheeky. We'll save that for later. Y equals sine x over x. Okay. That's our function. What are we doing with it to find its derivative?
We establish u and v.
Yep, establish u and v. What are they going to be?
Sine x and x.
Which one's which?
U is sine x and then v is x.
Good, yeah. This one does matter, which order you do it in. Okay, then from there, what else?
Find the derivatives now.
Yep.
But
U dash and V dash. What are they?
I think u dash is cos x.
Yep.
And then v dash is just 1.
That's it. Now for the fun bit, which is subbing things in. So y dash of x, still along the diagonals. What's the main difference? Well, I guess differences. Or maybe even, oh, no, go ahead.
Is it first x times cos x
Yeah, VU dash, so x cos x is going to be the start. Yeah.
minus sine x
Yep, minus 1 times sine x, which just becomes sine x. That's good.
all over x squared?
Yeah, all over x squared. Now, because x squared is the same thing as if I just said v squared, yeah, you might as well put it in. But you could imagine if this was like a whole like quadratic, it's like you'd rather just put a v in there and leave it. But yeah, that's that. That actually is our final answer. There's really nothing else to simplify there. Now, I guess this v was kind of nice to work with because yeah, you could split the fraction, but you shouldn't. Leaving it like that is perfectly acceptable. And that's that. Now here's the cheeky one that I was going to give. It's going to be quite similar. Sine x over cos x. Want to find the derivative of this. What are we doing?
Wait, Chris,
Yeah.
um, do we have to like find the derivative, or can we just solve on the spot?
Yeah. Mm-hmm.
Because I think this is like just tan x, right?
It is just tan. Yeah. Y equals sine on cos, which is tan. And then, of course, tan is 1 over cos squared x. Now, that was why I was saying it was cheeky. I want you to actually do this with the quotient rule, and then you'll see something. Well, actually, hang on. I wonder how complicated that'll be. We'll try it anyway. We'll try to do this with the quotient rule, and then you'll see where the derivative of tan actually came from. So, if we wanted to do this quotient rule style, what would we do?
We establish u as sine x and then v as cos x.
Yep. U is sine x, v is cos x.
And then u dash is cos x. And then v dash is negative sine x.
Yep, those are good. Now I'm very curious to see if we can get it to look like 1 over cos squared at the end. Let's find out. So, if we start writing these out, what's it going to be? You can already kind of see it.
Wait, um, is it just so obviously it's gonna be cos square x on the top,
Yep, that's our cos x times cos x. Yep,
and then um there's negative sine x squared, but a minus and a minus make a positive,
yep. So it'll
so it just
be minus sine squared x, which, yeah.
becomes a positive.
Yep.
And then it's all over cos squared x, and then the first term obviously gets cancelled out, and then you just get sine squared x over cos squared x.
Yeah, so you have, if you were to split the fraction, you'd get cos squared over cos squared, and you'd have sine squared over cos squared. This one, yeah, that's just going to be 1. This one, I mean, sine over cos is just tan. How do we make it look like it? Because when both of these are squared, you can take it all out, like all squared, and then it's just tan squared. 1 plus tan squared x. What can we do from there? Put these together. Oh, wait, no. I know what this is. Yeah, you can do that, and this is correct. That is a correct derivative. But there's this identity, cos squared plus sine squared equals 1. So you just replace that with 1, and that's how you make it look like the tan derivative. Does anyone remember where this is from? Anyone remember where this is from?
Pythagoras.
Yeah, Pythag. These are the same thing. So this cos squared plus sine squared being 1 is just what happens if you put Pythag on a unit circle. So you have your unit circle, it has radius 1, so your hypotenuse is 1. And then when you think about the triangle that's being created here, cos is the x and sine is the y. And so if you do your a squared plus b squared equals c squared, well, that's what sine squared plus cos squared equals 1 squared. And well, from there, 1 squared is just 1. So that's where that came from. But otherwise, yeah, so that's why that is that way that one was. So what we've seen is an equivalent way to do derivative of tan is to just do 1 plus tan x, or tan squared x. All right, you can do that if you wanted to just do derivative of tan. That's another way of doing it. In fact, if you have a look at the formula sheet that you get, you might have noticed there was also sec squared on the tan thing. That's just because 1 over cos is sec, and so, but that's more of a special thing. I don't know why they bothered putting this in the methods formula sheet. This will be probably the only time you see sec in methods ever, and it's just like not really. Actually, let's see, is it explained at all? Sec. May or may not actually see it. That's just a derivative. That's just seconds. Hey, look at that. They actually did it. Yeah, look at that. For convenience, we'll call this sec. Yeah, okay. I'll say that's good enough. But cool. So that's quotient rule. We can do, yeah, we'll do one more just to wrap up. Oh, actually, no, we will do one more. Y equals, oh, how bad do I want this to look? X squared over, what's an okay? No, we'll put a linear on the bottom. So we'll do something like cos x over 2x plus 1 all squared. That's what we'll do. All right. In fact, this is actually a good one because it can be done 2 different ways. We'll try to show both. But for now, we'll just try and do it the way that's most intuitive here, which is to what? We have a division of 2 functions. How do we normally solve derivatives with divisions?
We define u and v.
Define u and v. Yeah. Which one's u? Which one's v?
Cos x is u, and then 2x plus 1 squared is v.
Yep. All right. Next up.
You find u dash and v dash.
Yep. U dash
U dash is just negative sine x.
Uh-huh.
And then I think for this one we need to do chain rule.
We do, yeah. I will pull up the formula sheet version of the derivative table just so you can see that this one actually does have a spot directly on it for it. So either go through the full chain rule if you like, or just do this on the screen share.
Is it just 4 times 2x plus 1?
Yeah, that's it. 4 times 2x plus 1. For everyone else, it's because n2 comes out the front, but this a2 also comes out the front. 2 by 2 is 4, and then from there, power down the front, reduce it by 1, which is why the power of 2 is no longer there. And well, at this point, you can just chuck this through. Alright, and then from there, finish off the quotient rule, which is we're going to have what? This is where you'll see they get kind of nasty. And this is actually pretty common as far as how many terms we're going to have in this one. Alright, should probably have the actual quotient rule up for you to look at.
Negative sine x times 2x plus 1 squared.
Yeah. Minus sine x bracket 2x plus 1 all squared.
And hold on.
Yeah.
Minus cos x times 8x plus 4.
Yeah, that's it.
And then it's all over 2x plus 1 to the power of 4.
Sure is. Now, I don't want to write that a whole bunch of times. This is where I would start just saying v squared, because if you look at it, all the stuff that's going on here, this isn't doing anything. So you might as well just focus on your numerator and chuck it in at the end. Okay, so what do we actually do when we have all of this complication here? Yeah, what actually is the thing? Because usually when they do it in a way where there's like a 2x plus 1 here and a... Well, actually is a 2x plus 1 there. Maybe I shouldn't have expanded that out. Yeah, because if we had just left it as common factor of 4 out, what we would have had is... We'll have the 4 out the front, 2x plus 1, and we'll still have the cos, but just write it in a slightly different order. Cos, wait, it was cos? Yeah, cos x. And now from here, you can actually see you have a common factor, 2x plus 1 and 2x plus 1. So we can take that all the way out as a common factor rather than expand it, which is definitely the lesser of two evils. 2x plus 1 comes out the front of, so there's going to be a 2x plus 1 left over from that, minus sine x bracket 2x plus 1, and then that one's gone now, so you're just left with minus 4 cos x, and again all over v squared. Yes, there was a common factor, but we don't need to delete it immediately. Like, your v squared is going to be 2x plus 1 power of 4, which would cancel this out, but we'll just still work on this first, which would just be expand out the negative sine x through both of those, and then only will we chuck in our v squared. So y dash x, 2x plus 1, minus 2x sine x, minus sine x, that's expanded that out, minus 4 cos x. Since that bracket is expanded as far as it's going to go, now we can chuck in our v squared. So that's just this all squared. Oh, did that go blurry for too long? Bugger. Still not. There we go. There's our v. We're just going to square that again. So 2x plus 1 all to the power of 4. And at this point, I would literally get my eraser out and just knock this one out and then make this 4 a 3, because on paper I would not want to write any more of that, and maybe I would even erase that a little bit so it doesn't look like I erased it, just to be a bit cheeky. And so yeah, that will be how you do that one finally. Okay, that has hit time. Feel free to leave if you've got something to do. Otherwise, for those who want to stay, I'll quickly do and show what you might do if you don't want to do a quotient rule in this case. So for those who are leaving, have a good day. Otherwise, let's continue with this one. So we would have had cos x over 2x plus 1 all squared, cos x over 2x plus 1 all squared. There's a way to rewrite this to be a product rule, and that's if you use a negative index on this. Y equals cos x times 2x plus 1 to the power of negative 2. Now you have a product of two terms instead of a division. So basically all I wanted to say was, yes, you can do this as a product rule if you would like. You would be doing chain rule on this bit. So, this would be your U, this would be your V. Even though it's negative here, it's still power down the front, reduce it by 1. I won't do the actual arithmetic on that. That'll be more so if you'd rather do that. So yeah, you now have that tool available to you should you wish. If there's anything you want me to clarify from that, please let me know. Otherwise, this shall be the actual end of class. Take care.